Hi, I'm Surya Teja Manapati, one of the corresponding authors for the article Design of Progressive Monitoring Overhead Water Tank with paper submission ID 54. Water is an essential commodity that we use in our everyday life. It is important to not waste water because of the limited availability of freshwater resources. But at the same time, we should prevent consumption of contaminated water. With that, I would like to introduce you to the objectives of our research. We wanted to design a system that would achieve the following objectives. The first objective is to reduce water wastage due to overfilling of overhead water tanks, which we found is a major source of water wastage from our observation. The second objective is to prevent consumption of contaminated water. This is done through checking the water quality of water through a suite of water quality sensors and updating these water quality values on the server via IoT so that the user can go through these values and take the corresponding actions. And our final objective is to clean the overhead water tank periodically. One of the key insight of our research is that we were able to design a system that was fault tolerant due to incorrect sensor reading from the water quality sensors, so that the final output from these functionality of the system would not be constrained due to errors due to the from sensors. And our second key insight is that we were able to decrease the power consumption by checking the water level at certain intervals of time rather than checking it continuously. So this is the block diagram that we have used in designing our experimental setup. So we have used a Raspberry Pi 0W microcontroller to which we have uh, connected a ultrasonic sensor and a flow sensor which will measure the water level of the tank and the inflow of rate of water into the tank. At the same time, we have connected a pH sensor and turbidity sensor to the Raspberry Pi via Arduino Uno because Raspberry Pi does not have analog input and outputs. So we had to use a Arduino Uno. The Raspberry Pi is also connected to the power supply uh, for the water pump via a relay because we wanted to control the water pump in certain areas. And at the same time, we have connected the Raspberry Pi to a motor for cleaning the water tank. We have used a Firebase database for the IoT platform so that the user can get the data from the database via an MIT App Inventor for which we have linked the database. The physical layout of the system is depicted as shown in the left side of the slide. So we have considered a cylindrical water tank for which we have attached a red colored box at the bottom of the tank. The red colored box consists of the suite of sensors so that they can check the water quality, but at the same time they can be prevented from being damaged because of the water, and it is easier for maintenance as well. And as you can see to the right side of the slide, you could observe a blue colored box. This is where the motor for the tank cleaning mechanism is held, and the motor is connected to a big shaft through the, as you can see, to which we have attached brushes at the edges, so that as the motor is switched on, the brushes will rotate alongside the walls of the interior of the tank, so that the walls of the tank are also cleaned. So the architecture for the water quality is depicted in the flowchart shown to the left half of the slide. Initially, the system will check for the turbidity of the water. If if the turbidity value is within the nominal range, then the system will check for the TDS and pH values. If either of the if either of the tests pass, then it indicates that the water is pure. This is because TDS and pH for water are interlinked to each other. So, and if TDS is pure, then ultimately pH is also said to be pure. So it indicates that there is a fault or error in the sensor readings. So this is where the fault tolerance plays part. But if both TDS and pH show that the water is impure, then the system will say that the water is impure. Or if the turbidity of the sensor alone of the water alone fails to stay in the nominal range, then also the system states that the water is impure. The flowchart in the middle of the slide is depicted for the cleaning mechanism, where the system will take inputs from the uh, user via IoT, whether to clean the tank or not. So once the user activates the command, the motor for the tank cleaning will be switched on and it will rotate continuously for 10 minutes, where in that 10 minutes the water tank would be cleaned. This is a overall architecture of the working of the system, as you can see to the right half of the slide. So initially the system starts and checks if the water is below the lower threshold of the tank. If so, it will check for the water quality. If the water quality is pure, then it will check for the number of times the last time that the water tank was cleaned, which is indicated via the variable CT. But if the water quality is impure, it indicates that the tank is impure. So the system will start the cleaning process. So yeah, and here we wanted to focus on one practical aspect which might be a huge challenge. So sometimes there may be cases where the water at the water source of the water pump from which the water is drawn into the water tank may be empty. As a result, the pump may just pull air, and there are chances that the water pump may get damaged. To prevent that, we have fixed a flow sensor, and the system will check through the flow sensor continuously, so that if the value of flow sensor or the inflow of water into the water tank falls below a threshold, the water pump will be switched off and a message will be sent to the user via IoT. But if the uh, inflow is greater than the threshold, then the water pump is said to be working perfectly. Here as you can observe, initially we kept CT greater than or equals to 6. So here 6 means that we wanted to clean the tank for every week, but this variable can be changed accordingly. So yeah, after the water is checked and cleaned and the water tank is cleaned, we initiate a stopwatch. We initiate the variable capital T equals to 0, and the water pump will be switched on, and we assign the variable T1 equals to capital T by 10.5, where capital T is the time taken to fill the water tank previously in the previous attempt. So the way this capital T by 10.5 indicates that the water level needs to be checked for every 9.52% of the time taken to fill the water tank previously. So the water level will be checked for 10 times till 95.2% of the previous time. But after that, what we are doing is that we are setting the variable t1 equals to 10 seconds, because After the tank is filled by 95.2%, this is where the critical section occurs, where we don't want the water to overflow and be wasted. So once the water level is above 95.2%, the T1 variable is set to 10 seconds. But once after the water level reaches the upper threshold, the water pump is switched off and the time taken to fill the water tank is stored and used for the next cycle. After storing the value of T, the water quality is again checked, so that if there by chance there is any um, impurities or the water is impure, the user will get to know and he or she may take the corresponding actions. From our experiments, we found that the power consumption would be optimum when the system checks the water level for every 9.52% of the previous time taken for the motor pump to fill the tank without losing its functionality. We were also able to verify that the system would be working perfectly fine according to our fault tolerance algorithm. With that, I would like to conclude our presentation that the proposed system can deliver pure water and can work efficiently. I would also like to add that the system can be part of smart home automation and can be used for other purposes as well. Thank you.